In this video, we're going to calculate heat. So by the end of the video, you should be able to calculate heat, specific heat, mass, and change in temperature for any reaction. So the heat is given by the symbol Q, and it's measured in joules or kilojoules. If Q is positive, it's an endothermic reaction, heat's going into the system. And if Q is negative, it's an exothermic reaction, Q or heat is leaving the system. Recall that from the class packet that Q is based on the mass of the substance, the temperature of the change it undergoes, and the specific heat of the substance. So if we can go into detail, the more mass of the substance is, the more particles you have, the more heat you have to apply to change its temperature. The more you want to change its temperature, the more heat you'll have to apply. So if you're going from 0 to 10 versus if you went from 0 to 100, 0 to 100 doesn't take more Q, heat. And the specific heat of the substance is what the substance is made out of. So if it's made out of something like a conductor, like a metal, it's going to heat up pretty quickly, and if it's not a conductor like wood, it's not going to heat up as quickly. So that specific heat is the amount of heat required to raise the temperature of 1 gram of a substance 1 degree, so that they have everything in common except for what they're made out of, what particle they're made out of. And here's just a small chart. I mean, everything has its own specific heat, but here's a small chart of a couple of things, and it's showing you that liquid water has a really high specific heat. It takes a long time to heat up water because it needs so much heat to change. Whereas solid ice heats up a little quicker, and water vapor even quicker than that. And then you can go through, like air heats up quicker than that. Basalt and granite that you might know from earth science are a little better at heat conductivity. And then at the end you see iron, copper, and lead, pure metals, which heat up really well. They're called conductors because of that, and their specific heats are very low. The one that you need to use the most often for our labs is the specific heat of water, and that's listed on table B and in the last value. It's 4.18 joules per gram Kelvin or joules per gram Celsius, because the Celsius and the Kelvin scale change in the same values, right? If it goes up 10 degrees Celsius, it also goes up 10 degrees Kelvin, and so in that case, they could be interchangeable. And so the formula for calculating heat is on the back of your reference table, table T, and it shows you what each letter represents, Q being heat, M being mass, C being that specific heat for the substance, and T being the final minus initial temperatures. So we're going to do an example with me, and then you're going to do one on your own. How much heat is needed to raise the temperature of 500 grams of water by 15 degrees? So your first step might be to identify your known variables, that we know it's a mass of 500, that the C is on the reference table B as 4.18 joules per gram Celsius, and the delta T is 15 degrees because it's going up by 15 degrees. If you know them, then you're going to multiply them together to say that MC delta T is the mass 500 grams times the 4.8 joules per gram Celsius, so the grams cancel, times the 15 degrees, so the Celsius cancels. That's why joules is the only unit left. And if you check your sig figs, you should only have 2 sig figs because of the number 15 degrees. So I got 32,000 joules. If you want to change it to kilojoules, side note, you would divide that by 1,000 to get 32 kilojoules. At this point, I want to see if you can do something similar. And so I have the answer here, but I'm going to ask you for the setup. How many joules of heat are absorbed by 50 grams of water heated from 30.2 degrees Celsius to 58.6. So see if you can find the correct setup. So you would have to identify that the mass was 50, the C was 4.08 from the reference table, and the T was 28.4 degrees change by doing 58.6 minus 30.2. You would plug it into your calculation as 500 times 4.18 times 28.4. So hopefully you picked the correct answer. And when you actually do this in your calculator, you're going to get a really long number. Remember, we don't calculate a ROMIT. We want to look at the numbers given to us that seem to be all 3 sig figs and round this number to 3 sig figs. What we're going to do now is go through a couple of other examples. So instead of calculating for joules, we're going to be calculating for either mass, C, or delta T. So I just want to show you one of each. So if you're calculating 520 joules heat added to water at 20 degrees and it went to 30 degrees, what's the mass of the water that you were heating? So what you could do is identify your knowns and unknowns again, and then plug them into the Q equals M to delta T formula in order. So the Q is 520, the M is unknown, the C from the reference table is 4.18, and the delta T was 10 degrees from 30 to 20. And so if you divide out 520 divided by 4.18 and divided by 10, with 3 sig figs, we get 12.4 grams were heated. So you can solve for M. And the next one, we're going to solve for specific heat. When 77 joules of heat are added to 10 grams of substance unknown at 20 degrees, The final temperature is 25 degrees. What's the specific heat of this unknown substance? So again, you should probably identify your unknowns, or you either write them out, circle them, or underline them. And then write your formula out so you can plug them in order. Q is 77, M is 10 grams, C is unknown because we don't know what the substance is, and the delta T was, sorry, I didn't write it over here, but the delta T was from 20 to 25, so 5 degrees. If we plug them all in, we didn't use C of 4.18 because that's only for water. We're solving for C, and we get a 1.5. Comparing it to water C, though, it seems to heat up much better than water does. Let's try one more type of example, solving for final temperature. So here's an example. When 418 joules of heat are added to 10 grams of water at 20 degrees, what will be the final temperature of the water? So again, identifying unknowns by either writing them out or circling them is pretty important. Writing them underneath each symbol could be another way of doing that. So Q is 418. The mass of the sample of water is 10. And the specific heat of water is 4.18. We're going to solve for delta T because it's unknown. Don't try putting in the 20 degrees yet. It makes the calculation actually a little harder. So if you solve for delta T, I got 10 degrees, and we reread the question. Remember it said it was added to. So that means if you started at 20 and you added heat, it should go from 20 to an additional 10 or 30 degrees. You should read that really closely because sometimes the questions will say something like the heat was removed from. In that case, if it said the same exact numbers but said removed from, you would have taken away 10 and went to 10 degrees as your final answer. At this point, you should be able to calculate heat, specific heat, mass, and change in temperature of any reaction.